Somewhere in the vast structure of the cosmos, there are regions so empty that entire galaxies almost vanish from the map. But even the emptiest place in the universe is not truly nothing. It still holds a mystery that astronomers have not fully solved. Tonight, this journey moves into the deepest known voids of space to explore what is there, what is missing, and why emptiness itself may reveal how the universe is built. If this kind of calm cosmic mystery belongs here, please like the video, subscribe to the channel, and begin the journey. The observable universe is the widest region available to human study. It is not the whole universe in a final or complete sense. It is the portion from which light has had time to arrive since cosmic expansion begins in the hot early state that astronomy describes as the Big Bang. Within that reach, matter spreads across distances so large that ordinary human scales disappear at once. Planets and stars become small details. Galaxies become common units, clusters of galaxies, where many galaxies gather under shared gravity, become landmarks. Between those landmarks lie vast stretches where galaxies grow rare. In this widest setting, the emptiest place in the universe does not first appear as a single destination. It appears as part of a pattern. At the broadest scale, the observable universe is neither a random scatter nor a smooth mist. It has structure. Astronomers describe that structure as a cosmic web. A web is a useful image because matter is not spread with equal thickness everywhere. It gathers into long filaments, broad walls, dense knots, and great open regions between them. The dense knots hold rich galaxy clusters. The filaments stretch across immense distances and connect one crowded region to another. The open regions between them contain much less visible matter. When large galaxy surveys map the sky in 3 dimensions, this pattern becomes clearer. The result does not resemble a packed ocean of galaxies. It resembles a landscape shaped by gravity, where crowded ridges and deep hollows share the same vast frame. This great arrangement emerges slowly over cosmic time. In the early universe, matter is far more even than it is now, though never perfectly even. Tiny differences in density are present from the beginning. One region holds a little more matter than another. Gravity, the force that pulls matter together, gives those small differences time to grow. Where matter begins slightly denser, more matter drifts in. Where matter begins slightly thinner, material leaves more easily for denser surroundings. Over billions of years, the contrast increases. Dense regions become richer, thin regions become thinner. The cosmic web forms through this patient sorting of matter, and the largest underdense places arise naturally within that process. From this outer view, emptiness is not a break in the laws of nature. It is one result of those laws working over enormous spans of time and distance. The universe builds crowded places and sparse places together. One does not exist without the other. A filament becomes meaningful because a lower density region lies beside it. A galaxy cluster appears more prominent because its surroundings can be far less populated. The eye, or the telescope, notices emptiness through contrast. Where galaxies line up in chains and gatherings, the gaps between them begin to stand out. Those gaps can expand to astonishing size. Some span tens of millions of light years. Some extend much farther. Yet even at this level, the emptiest known regions are not outside the cosmic pattern, they belong to it. The observable universe also has no preferred center in this map. From Earth, the sky surrounds every direction equally, and large surveys reveal structure in all directions rather than a single grand arrangement with one middle point. This matters because the emptiest place cannot be understood as a borderland beyond the normal universe. It is an interior feature of the visible cosmos, embedded within the same expanding space that carries galaxies apart on the largest scale. That expanding space does not move galaxies through a fixed external void. Instead, it changes the distances between far regions of the cosmic web itself. The web and its empty reaches are both part of the same expanding geometry. Light needs time to cross the universe, so looking far away also means looking deep into the past. A distant galaxy is seen not as it is now, but as it is when its light begins its journey. The wide map of the observable universe is therefore a map across both space and time. Nearby regions show a later stage of structure growth. More distant regions show earlier stages. Even so, the broad lesson remains steady. Matter does not remain evenly spread. It gathers, stretches, and leaves behind large underfilled regions. This repeated pattern helps astronomers understand that cosmic emptiness is not an accident of one unusual place alone. It is part of the universe's general architecture. Within this architecture, ordinary language can mislead. The phrase empty place suggests a location stripped of all content, like a perfect blank. The observable universe does not present that kind of simplicity at large scale. Even where galaxies are scarce, space still belongs to a wider network of matter, radiation, gravity, and motion. The great underdense regions are real, but their reality becomes visible first as low population within a mapped structure, not as pure nothingness. This first outer region therefore asks for care in description. The emptiest place in the universe is best approached not as a hole punched through reality, but as the deepest known reduction in a universe that remains structured everywhere. Seen from the widest perspective, the cosmos becomes a balance between abundance and scarcity. Bright galaxies fill catalogues in the millions. Clusters gather with enormous mass. Filaments span distances beyond ordinary imagination. Yet volume is dominated not by the crowded knots, but by the thinner regions between them. Much of the observable universe consists of space where visible galaxies are widely separated, and where matter is less concentrated than average. That fact gives emptiness a central role in the large cosmic picture. These sparse regions are not minor leftovers around the edges of more important places. They help define the shape of the whole. In this outermost view, the mystery begins quietly. The observable universe presents a grand map whose brightest features are easy to notice, but its most revealing features may be the dark intervals between them. The web is legible because it contains openings. The largest openings create a calm and lasting scientific problem. Astronomers seek to understand how far a real region can fall below the cosmic average in matter and galaxies while still remaining part of the same physical order as everything around it. That problem rests first on scale, pattern, and structure. It belongs to the widest view before it belongs to any single named void. Here, at the outer edge of the topic, the universe appears as an immense connected arrangement, and within that arrangement, emptiness already has form. The large structure of the observable universe does not begin as a finished web. It develops gradually from a young cosmos that is far smoother than the one seen today. In that early state, matter and energy fill space with remarkable uniformity, yet not with complete exactness. Very small differences are present from place to place. One region contains slightly more matter than another contains slightly less. Those differences are tiny, but they matter because gravity responds to them faithfully. It does not need large contrasts in order to begin its work. Given enough time, Even slight unevenness can grow into a grand pattern. Gravity acts as the patient organizer of the large-scale universe. Where matter is a little denser, its pull becomes a little stronger. That slightly stronger pull draws in more surrounding matter. As more matter arrives, the pull increases again. This does not happen as a sudden collapse across all scales at once. It proceeds over immense stretches of time while cosmic expansion continues everywhere. Expansion increases distances on the larger scales, while gravity works locally and regionally to gather material. The shape of the cosmic web emerges through this balance. Expansion keeps the universe broad and dynamic. Gravity sculpts denser features within it. A useful way to understand this process is to imagine the young universe not as empty space with isolated objects floating in it, but as a widespread field of matter with subtle hills and shallow valleys in density. The hills are only slightly raised at first. The valleys are only slightly lowered. Over billions of years, gravity amplifies those gentle differences. The hills gather more mass and become the foundations of future filaments, walls, and clusters. The valleys lose matter toward the denser surroundings and become the broad underfilled regions that astronomers later identify as voids. In this way, the web and the empty regions are not separate inventions. They are twin results of the same process. Dark matter plays a central role in this shaping. It is called dark because it does not emit, absorb, or scatter light in the ordinary way, so telescopes do not see it directly. Its presence is inferred from gravity and from many kinds of observation across cosmology and galaxy studies. On large scales, dark matter provides much of the mass that helps structure form efficiently. As the universe evolves, dark matter gathers into an invisible framework of denser and thinner regions. Ordinary matter, made of atoms that later form gas, stars, planets, and galaxies, responds to that gravitational framework. It falls into the deeper gravitational wells and becomes more concentrated there. The visible web of galaxies therefore traces a deeper underlying pattern that gravity builds with the help of dark matter. This does not mean that matter simply rushes in straight lines toward a few central points. The process is richer and more distributed. Matter streams along preferred directions set by the surrounding gravitational landscape. Some regions collapse more strongly in one direction first, forming sheet-like structures. Other regions become elongated and produce filaments. Where several such channels meet, clusters grow. Between them, broader zones are steadily drained. The cosmic web is therefore not only a collection of dense nodes, it is a connected system of pathways and boundaries, shaped by how mass flows over cosmic time from less dense environments into more dense ones. As matter leaves the underdense regions, those regions do not remain static. They expand relative to their surroundings. This is one of the most important features of the web's growth. A dense region resists expansion more effectively because gravity there is stronger. A less dense region offers less resistance and can thin out further as the universe evolves. The result is a growing contrast. Crowded places become more prominent, sparse places become more open, the cosmic web sharpens. What begins as modest unevenness turns into a striking arrangement visible in large galaxy maps. This is why emptier regions can become immense without requiring any exotic break from known physics. They arise because matter flows away from them over long intervals, while denser structures continue to strengthen nearby. This process also explains why emptiness on cosmic scales is relational rather than absolute. A void develops because surrounding structures gain matter and definition. A filament becomes brighter in contrast because nearby space becomes thinner. A cluster seems especially rich because matter from a large surrounding volume has helped build it. The web is not assembled piece by piece like separate objects placed into a background. It grows as a single connected pattern in which each region influences the fate of its neighbours. Density drains from one place and enriches another. The shape of the whole becomes legible through this exchange. The ordinary matter that later shines as stars follows this broader history. At first it remains largely as hot gas. Over time it falls into dark matter halos, cools in suitable environments, and helps form galaxies. Those galaxies then mark the denser parts of the web in ways astronomers can observe directly. Yet the galaxies are only the visible traces of a larger structure. They reveal where the gravitational gathering has been most effective. They also reveal where it has been least effective, because the great sparse spaces between bright concentrations show where galaxy formation becomes much rarer. In this sense, visible galaxies work like lanterns outlining a terrain whose deeper mass distribution extends beyond what light alone can show. Nothing in this development is hurried. The web takes shape across cosmic ages. The larger structures require long growth, steady motion, and the continued action of gravity under expansion. This slowness matters to the tone of the subject. The emptiest regions of the universe do not open like sudden wounds. They deepen gradually as matter responds to the long-term geometry of the cosmos. Their mystery begins not in violence but in patience. The same patient process that builds clusters and galaxies also leaves behind regions of extraordinary sparseness from this regional view. The web of matter becomes the essential environment for understanding cosmic emptiness. The sparse zones are not mistakes, tears, or places where the universe fails to exist. They are the expected low-density side of structure formation. Gravity shapes abundance and scarcity together. The universe does not merely contain voids after the web is built. It builds the web by creating contrast between denser and thinner regions at the same time. In that sense, emptiness is not outside the structure. It is one of the structure's defining products. A cosmic void is a region of the large-scale universe where galaxies are far less common than average. The word void can sound absolute, as if it refers to a place stripped clean of all existence. But in astronomy it has a more careful meaning. It describes a vast underdense region, which means a region with much lower density of matter than the cosmic mean. Density, in this setting, is simply the amount of matter present within a given volume of space. A void is therefore not defined by total absence. It is defined by strong scarcity across an enormous scale. Once astronomers begin to map the universe in 3 dimensions, these regions become impossible to ignore. The bright concentrations of galaxies do not fill the observed cosmos uniformly. They gather along connected structures, and between those structures lie broad interiors where the galaxy count falls sharply. Some of these interiors are modest in size by cosmic standards. Others are immense. The largest known examples stretch across distances so great that even a beam of light, moving at its full speed, would require hundreds of millions of years to cross them. In that sense, a giant void is not a gap between neighbouring objects. It is a major region of the cosmic landscape. These regions are often described as the emptiest places in the universe, and that description is understandable, but it needs discipline. What makes a void remarkable is not the presence of literal nothingness. What makes it remarkable is scale combined with rarity. A small empty patch inside a galaxy is not a cosmic void. A wide zone between a few local galaxies is not necessarily a void in the formal sense. A true cosmic void occupies a large coherent region within the cosmic web, and remains significantly below average in the amount of matter and in the number of galaxies found inside it. It is a feature of the universe's grand architecture, not a local curiosity. Astronomers also find that voids are not rare exceptions. They're common components of the large-scale pattern. Dense structures such as clusters and filaments attract attention because they shine with galaxies, stars, and hot gas. Yet by volume, the universe is dominated not by the crowded knots, but by lower density space. Much of the observable cosmos lies in or near underdense environments. This means that giant voids are not small pockets squeezed between more important places. In terms of sheer volume, they are among the major settings in which the universe is organized. A useful mental adjustment happens here. Human attention naturally moves toward what is bright, heavy, or crowded. In the night sky, luminous galaxies invite notice. In scientific images, dense structures stand out at once. But the deep pattern of the universe becomes clearer only when attention settles on the spaces between those bright structures. The voids help reveal the shape of the web by providing contrast, and they also preserve a record of how matter moves over cosmic time. A giant void shows where mass does not gather efficiently. It marks where the long history of gravitational growth leaves behind a region of unusual sparseness. Even the shape of a void resists overly simple imagination. A void is not usually a perfect sphere carved neatly into space. Its boundaries can be irregular. Its interior can be smoother in some directions than in others. Some voids join or overlap in ways that make them appear as parts of larger underdense complexes. Others contain internal gradients, with the deepest scarcity near the middle and somewhat richer populations near the outer parts. The term void therefore names a real class of region, but not one with a single exact geometry repeated everywhere. Nature allows broad family resemblance rather than rigid uniformity. The largest of these regions can also influence the motion and distribution of galaxies around them. Galaxies near the edges of a void tend to reside in denser boundary structures, while the inner volume contains far fewer systems. Over long timescales, matter effectively drains outward from the void interior towards surrounding filaments and walls. This makes the contrast between inside and outside more pronounced. The realm of giant voids is therefore not still in a simple sense. It participates in the ongoing evolution of the cosmic web. Sparse regions continue to expand in relative terms, while denser regions continue to gain structure. The word giant is also important. On Earth, an empty field feels large. In a galaxy, a cavity of gas can seem vast. In cosmology, a giant void occupies a very different order of scale. Its dimensions are measured not in the size of planets or solar systems, or even single galaxies, but in distances between large galaxy populations. These are regions so broad that they can contain only a few galaxies where many more might otherwise be expected. To describe such a place as empty is not to deny that something remains within it. It is to acknowledge that the difference from the cosmic average is profound. This broader definition helps avoid a common mistake. Empty space in ordinary speech sounds like a blank stage on which matter appears only here and there. The cosmic void is not a blank stage. It is a measurable feature within an active universe, shaped by history, bounded by structure, and described in relation to average density. It belongs to cosmology not because it lacks meaning, but because its lack of matter has meaning. It tells astronomers how structure grows, how gravity redistributes material, and how the visible universe comes to have strong contrast between crowded and sparse regions. Another important feature of giant voids is that their significance does not depend on a dramatic visual appearance from within. A traveller placed inside one would not necessarily see a dark chamber with sharp walls. The nearest galaxies might simply be very far apart. The sky would still contain light arriving from distant directions. The void exists as a large statistical and structural reality, more than as an enclosed room. It is identified by mapping and comparison. That is why the idea of a void belongs to measurement as much as to imagination. In this regional view, the universe reveals a quiet truth. Its emptiest known places are not singular miracles. They are part of a class of enormous underdense domains that arise naturally within cosmic structure. They occupy a large share of volume, they deepen the contrast of the cosmic web, and they remind astronomy that absence can be as informative as presence. A giant void is not the end of structure. It is one of structure's most expansive expressions. A cosmic void becomes visible through its boundaries. The sparse interior matters, but the eye and the instrument both first recognize it by contrast with what surrounds it. Around many voids, galaxies do not fade away gradually into a featureless background. They gather into brighter, richer arrangements that outline the emptier region beside them. These boundaries can take the form of walls, filaments, and denser galaxy groupings. Together they act as the visible frame around a lower density interior. In this way, nothing is not seen alone. It is seen because something more crowded stands nearby. The word wall is useful, though it must be handled carefully. A wall in everyday life suggests a flat, solid barrier with a clear surface and a sharp edge. A cosmic wall is not solid in that sense. It is a broad region where galaxies are more concentrated than average, and where the distribution of matter becomes noticeably richer than in the neighbouring void. It can stretch across immense distances and may contain many galaxies, groups, and clusters arranged in a sheet-like pattern. When astronomers map the large-scale universe, such walls appear as luminous boundaries that help define the darker hollows between them. Filaments serve a related role. These are long, thread-like structures of enhanced density that connect larger concentrations of matter. They are not thin like wires by human standards. They can be extremely wide and extend over immense reaches of space. But compared with the great emptiness beside them, they still appear as drawn strands of structure. A filament can trace the edge of a void, connect one galaxy cluster to another, or branch through a broader wall-like region. When several filaments surround or border an underdense space, the void begins to stand out not merely as a region with fewer galaxies, but as an organized absence enclosed by an organized network. This contrast reveals an important truth about the cosmic web. The boundaries of a void are not decorative edges added after the fact. They are part of the same process that creates the void itself. As matter flows away from lower density regions over cosmic time, it does not vanish. It accumulates in the surrounding structures. The edges brighten because the interior thins. The wall grows richer because the neighbouring space gives up material more easily. The filament strengthens because matter prefers the gravitational roots that draw it into elongated structures. Boundary and interior therefore develop together. The outline of emptiness is built by the movement of matter toward places that are less empty. The effect can be striking in large galaxy maps. A survey may show hundreds or thousands of galaxies gathered in chains and sheets, while next to them lies a broad volume with very few. The boundary does not always form a perfect enclosure. It can be broken, uneven, or partial. Some walls are more complete than others. Some filaments curve and split, suggesting a complex edge rather than a single clean surface. Yet even with this irregularity, the overall contrast remains clear. A denser lattice marks the zone around a more weakly populated interior. That is enough for the human mind and for quantitative analysis to begin identifying a void. The galaxies found along these boundaries also tend to differ in environment from the few galaxies that may lie within a void interior. Near the boundary, gravity has had greater success in drawing matter together. Groups and clusters become more common. Galaxy interactions are more likely. Gas can be more plentiful in concentrated regions. The boundary thus acts not only as a geometric outline but also as a transition in environment. It marks where cosmic conditions become more favourable for the growth of richer galactic structures. Even without stepping into the interior itself, the boundary already tells a story about uneven cosmic development. Light plays a subtle role here. A void is not outlined by a glowing membrane. There is no luminous shell shining because the universe wishes to display its architecture. The apparent edge comes from the accumulated light of many galaxies positioned in denser arrangements. Each galaxy shines for its own local reasons, through stars and gas, and the physical processes within it. Yet on large maps, their collective distribution creates the appearance of bright contour lines around darker spaces. The universe therefore presents its emptiness through the placement of ordinary luminous matter. A wall around nothing is still made of galaxies. These boundaries also help astronomers decide where a void begins and ends. Though that decision is never perfectly simple, a void does not usually possess a hard surface like the edge of a planet or the shoreline of an ocean. Instead, the density changes across space, sometimes gently and sometimes more rapidly. The surrounding wall or filament offers a practical guide because it indicates where the distribution of galaxies becomes significantly richer. In many cases, the edge of a void is best understood as a transition zone rather than a razor line. The wall is real, but it is broad. The contrast is measurable, but it is not infinitely sharp. This broadness gives the boundaries a quiet complexity. From far enough away, a wall may seem like a single feature. On closer examination, it resolves into chains of galaxies, linked groups, denser knots, and thinner stretches between them. A filament may seem smooth in a simplified map, yet detailed surveys show local variation along its length. The edge of emptiness is therefore textured. It is made of many individual systems participating in a larger pattern. The boundary teaches the same lesson as the web itself. Cosmic structure is hierarchical, with smaller arrangements nested inside larger ones. In a deeper sense, the walls around voids make emptiness legible. Without them, the low-density region would be harder to define. A sparse interior seen in isolation could seem like a mere lack of information or a temporary absence of detected galaxies. The surrounding concentration removes that uncertainty. It shows that the emptiness belongs to a wider pattern of contrast. A wall is not only matter piled up near less crowded space, it is evidence that the less crowded space is real as a region. It gives shape to absence. Here, the study of the emptiest places remains at the level of boundary and outline. The focus stays on the richer structures that frame the hollows of the cosmic web. These walls and filaments do not hide the void, they reveal it. Their brightness, density, and connection make the sparse interior readable on the grandest scales. In the universe, even the deepest quiet becomes visible through what gathers at its edge. Among the many underdense regions of the cosmic web, a smaller class draws special attention because of its extraordinary scale. These are often called supervoids. The term is not always fixed by one universal boundary accepted in exactly the same way by every study, but its practical meaning is clear enough. A supervoid is a very large cosmic void, broader and more extreme than the more common examples found throughout galaxy surveys. It is a contender for the title of emptiest known place, not because it contains absolute nothingness, but because it combines immense volume with unusually low density over a coherent region. The step from ordinary void to supervoid is important because scale changes the scientific meaning of the region. A smaller void already tells astronomers that matter does not gather evenly. A supervoid suggests something larger in the growth of cosmic structure. It represents a major domain of the universe in which matter, and especially visible galaxies, becomes scarce across a span so broad that the region affects how the surrounding cosmic map is interpreted. A giant underdense zone does not stand as a mere blank interval between nearby bright structures. It becomes a dominant feature in its own right, large enough to influence how astronomers think about density, contrast, and the evolution of the web on the grandest scales. Not every large, sparse region automatically becomes a supervoid candidate. Astronomers look for several features together. The first is size. The region must extend over an immense volume, far beyond what would be described as a modest local gap. The second is coherence. The low-density character should persist across the region, rather than being produced by a few disconnected sparse patches that only seem linked from a limited viewpoint. The third is depth. The matter density, or the number of galaxies used as visible traces of matter, should fall substantially below the cosmic average. When those qualities combine, the region begins to stand out as a candidate for the most extreme emptiness that has yet been mapped. Even then, the word emptiest remains more delicate than it first appears. One candidate may span a larger volume, while another may be somewhat smaller but lower in density at its core. One may seem emptier when judged by bright galaxies alone, while another may appear more extreme when additional traces are considered. This makes the ranking of cosmic emptiness less simple than naming the tallest mountain or the largest planet. The universe does not always present a single champion in a clean and final way. Instead, it offers a group of contenders whose status depends on measurement, definition, and the specific meaning assigned to the word empty. This is why supervoid candidates often carry a quiet uncertainty, even while they remain scientifically real. A region can be strongly underdense without having perfectly known boundaries. It can appear extreme in one survey and somewhat less extreme in another, depending on how galaxies are counted, how distance is inferred, and how the surrounding cosmic average is defined. Some candidate regions may also consist of multiple neighbouring voids that partially merge into a broader underdense complex. In such cases, the candidate remains impressive, but the question shifts from whether the region is sparse to how its internal structure should be described. Is it one enormous hollow, or a connected family of hollows? The answer is not always obvious. Supervoid candidates are therefore rare not only because the universe does not create them often, but also because identifying them requires wide and careful mapping. A small survey may capture only part of a large underdense region. An incomplete catalogue may miss faint galaxies and make a place seem emptier than it is. A different survey depth may reveal that a supposed single supervoid has a more complicated inner arrangement. These limitations do not erase the importance of the candidates. They simply remind astronomy that the emptiest places must be approached with patient measurement, rather than dramatic certainty. The interest in these regions grows further when astronomers compare them with other large-scale cosmic signals. A very broad, underdense region can influence the passage of light through the evolving universe in subtle ways. It can also affect the local pattern of galaxy motion and the distribution of structure around it. Because of this, a supervoid candidate is not important only as a place with few galaxies. It is important as a large physical environment whose thinness may leave detectable traces in the wider cosmic record. A truly enormous sparse region becomes a laboratory for understanding how the largest structures and the lowest density domains evolve together. There is also a psychological reason these candidates attract attention. Human thought is often drawn to extremes. The hottest star, the largest black hole, the farthest galaxy, and the deepest void all offer a way to test the range of nature. In cosmology, the supervoid candidate serves this role for emptiness. It asks how low the density of a real cosmic region can become while remaining part of the ordinary structure formation of the universe. It does not invite fantasy, it invites comparison. By studying the most extreme sparse regions, astronomers learn not only about those regions themselves, but about the rules that produce all lesser voids as well. Some candidate supervoids become well known because they are especially broad or because they appear in connection with unusual features in the cosmic microwave background or in the arrangement of surrounding galaxies. Others remain less famous but still matter scientifically, because they expand the sample of extreme low-density environments. This broader family is useful. A single famous case may attract public attention, but science becomes stronger when several candidates can be compared. One region may be larger, another may be emptier in its central portion, another may have better survey coverage and therefore firmer statistical support. Together they show that cosmic emptiness is not one isolated marvel, but a spectrum with rare extreme members. The realm of supervoid candidates therefore sits between general theory and specific example. It narrows the subject from the many ordinary voids of the cosmic web to the rare regions that seem to approach the lowest densities known on the larger scales. These candidates are not defined by spectacle alone. They earn their place through size, coherence, scarcity, and careful comparison with the cosmic mean. They remain candidates because measurement is never perfect, and because emptiness itself requires definition. Yet their importance is clear. They show that the universe can produce regions of astonishing breadth, where matter becomes profoundly thin, and they establish the class of places from which the emptiest known domain must be sought. Among the named voids of the large-scale universe, the Boötes Void holds a special place in the scientific imagination. It is not the only immense underdense region known to astronomy, and it is not the final word on cosmic emptiness, but it becomes one of the most famous because it presents the idea of a giant void in a form that is easy to grasp. It is large, striking, and memorable. It lies in the direction of the constellation Boötes, and its name gives a specific identity to a type of region that might otherwise remain abstract. Through this one place, the broader concept of cosmic emptiness becomes concrete. The Boötes Void is often described as one of the largest known voids in the observable universe. Estimates of its scale vary somewhat depending on how its edge is defined and how the surrounding structures are measured, but the general picture remains consistent. It spans a distance on the order of hundreds of millions of light years. This alone gives the region its extraordinary character. A void of such extent is not merely a broad gap between bright systems. It is a genuine cosmic province, a domain large enough to reshape ordinary intuition. When a place is described in these terms, emptiness stops meaning local absence and begins to mean structural vastness. Its fame also comes from contrast. The Boötes Void is not important because it is blank in an absolute sense. It becomes important because a region so wide contains far fewer galaxies than would normally be expected in a comparable cosmic volume. This scarcity makes the region stand out against the richer distribution of galaxies around it. The emptiness is statistical and structural. It is seen in the reduced density of luminous systems across a huge span. That is enough to make the Boötes Void one of the most powerful examples of how the universe can organize matter unevenly on the grandest scales. The name carries a calm and slightly ancient quality, because Boötes itself is an old constellation name, inherited through long traditions of sky observation. Yet the void is not ancient in the sense of being known for centuries. It belongs to modern cosmology, to the era in which astronomers build wide galaxy catalogues and begin to understand the three-dimensional architecture of the universe. Its recognition marks a moment in which cosmic scale becomes newly visible. Before such mapping, the sky can suggest richness everywhere because galaxies appear as separate lights across many directions. The Boötes Void helps reveal that between those lights, and between the structures they form, there can be expanses of remarkable sparsity. Part of what makes the region iconic is that its scale almost resists language. The mind can picture a galaxy, however imperfectly. It can picture many galaxies gathered in a cluster. It struggles more when asked to picture a region where expected galaxies largely fail to appear, across a span that light itself needs hundreds of millions of years to cross. At that size, the Boötes Void becomes less like a gap and more like a broad interior of the cosmic web, where the usual abundance of luminous systems gives way to unusual thinness. It teaches scale by withholding the objects that might otherwise fill it. Even so, the Boötes Void is not empty in the everyday sense. It contains galaxies, though very few compared with a more typical region of similar size. This detail is essential. The famous sparse population inside the void does not weaken the concept of the void. It clarifies it. The Boötes Void is not a chamber of perfect nothingness. It is a domain of profound underdensity. A few galaxies remain, scattered and isolated compared with the richer boundaries outside. Their existence shows that even one of the best-known giant voids still belongs to the ordinary universe of matter, gravity, and cosmic history. The region is extreme, but it is not outside known nature. Its reputation grows in part because of that delicate balance between emptiness and persistence. If the region were simply full of galaxies, it would not matter. If it contained absolutely nothing and stood apart from the rest of cosmic structure, it would belong more to fantasy than to cosmology. Instead, it lies in the productive middle ground where structure becomes thin enough to astonish while still remaining measurable and real. The Boötes Void therefore becomes a symbol of how the universe reaches extremes without abandoning continuity. It is one of the clearest cases in which scarcity itself becomes a major cosmic feature. Astronomers also find the region memorable because it helps translate abstract theory into observed reality. The theory of large-scale structure predicts that gravity should create both concentrations and underdense interiors as the universe evolves. The Boötes Void gives that expectation a famous face. It demonstrates that immense sparse regions are not just mathematical possibilities, they are mapped components of the actual sky. In this sense, its importance is both scientific and educational. It gives a name and a location to a concept that might otherwise remain diffuse in public understanding. The surrounding structures matter here as well. The Boötes Void does not float without context. It is defined by the galaxies and denser arrangements that frame it. The contrast between its sparse interior and the richer surroundings allows the void to be identified as a coherent region. This makes its fame inseparable from the wider cosmic web. The Boötes Void is not a lonely exception standing apart from the universe's normal form. It is an especially dramatic expression of that form. The same web that builds clusters and filaments also permits a hollow on this scale. Because of this, the Boötes Void often becomes the first named example invoked whenever people discuss the emptiest place in the universe. It is large enough to be impressive, famous enough to be remembered, and clear enough in concept to anchor broader discussion. Yet the calm scientific view remains careful. The void is iconic, but not magical. It is immense, but not infinite. It is deeply underdense, but not perfectly empty. Those distinctions matter because they preserve the real achievement of the subject. The universe does not need absolute nothingness in order to produce wonder. It only needs enough contrast, over enough distance, for emptiness to become visible as part of structure. In this named region, cosmic emptiness takes on one of its most enduring forms. The Boötes Void stands as a vast, quiet territory within the observable universe, memorable not because it breaks the rules of cosmology, but because it follows them so fully that their results become almost difficult to believe. It remains one of the great landmarks of the sparse cosmos, a place where the absence of galaxies over immense distance becomes one of the clearest signs that the universe builds itself through both gathering and withdrawal. A giant void is not found by looking at one dark patch in the sky and declaring that nothing is there. The sky can seem uneven for many reasons. Dust can block light. Telescopes can miss faint objects. A region may appear sparse simply because it has not been surveyed deeply enough. For this reason, the mapping of a true cosmic void depends on method rather than impression. Astronomers must measure where galaxies lie in 3 dimensions. Only then can a broad, underdense region emerge as a real structure instead of a visual guess. The first step is to move beyond the flat appearance of the night sky. From Earth, celestial objects are spread across directions, but direction alone does not reveal distance. 2 galaxies may appear close together on the sky, while actually lying very far apart along the line of sight. Another pair may seem separated in angle while belonging to a similar depth in space. A void cannot be defined from a 2-dimensional picture alone because its emptiness concerns volume, not only direction. What matters is not merely where galaxies appear on the sky, but how they are distributed through the vast depth behind that sky. This is where redshift becomes essential. Redshift is the stretching of light toward longer wavelengths as the universe expands. For distant galaxies, larger redshift usually means greater distance. Astronomers measure the light from a galaxy, study how known spectral features are shifted, and use that shift to estimate how far away the galaxy is within the expanding cosmos. Once many such measurements are collected, the ski gains depth. Galaxies can then be placed not just on a celestial surface, but within a 3-dimensional map. The great sparse regions of the universe begin to appear only after this depth is added. Early wide redshift surveys transform the understanding of large-scale structure because they show that galaxies are not scattered like isolated points in a nearly uniform sea. Instead, the maps reveal arcs, chains, walls, and major open interiors. One of the most important visual tools in this work is the cone diagram. In such a diagram, a slice of the sky is shown with distance extending outward from Earth. When many galaxy redshifts are plotted this way, structure becomes strikingly visible. Dense groupings appear as clustered bands and curved ridges. Between them lie broad spaces with few plotted galaxies. The void is not seen as a black object. It is inferred from the absence of expected points within a mapped region. This method gives the discovery of giant voids its distinctive character. The astronomer does not stare into a cosmic hole with a direct image. Instead, the astronomer builds a catalogue, measures distances, plots positions, and notices that a large volume contains far fewer galaxies than neighbouring regions. Emptiness arrives through accumulation of evidence. Each galaxy added to the map sharpens the boundaries of where galaxies do gather and where they largely do not. The void becomes visible by patient comparison between occupied and under-occupied space. The Boötes Void enters astronomy through exactly this kind of mapping. In the early modern era of redshift surveying, astronomers gather the data needed to trace the large structure of the nearby universe more faithfully than before. In that process, a remarkable underdense region in the direction of Boötes becomes clear. It is not a simple missing patch caused by poor observation. Its scale and coherence stand out in the mapped galaxy distribution. The region is later examined in more detail, and its identity as a major void is strengthened. What makes the finding memorable is not merely that one odd region looks sparse, but that a survey based on measured distances reveals a huge volume with far fewer galaxies than expected. The act of mapping also requires statistical discipline. A void is not declared on the basis of one or two missing galaxies. Astronomers compare the number density of galaxies in a region with the number expected from the wider survey. They ask whether the scarcity is coherent across a large connected volume. They examine whether the result survives improved coverage and whether the boundary structures around the region support the interpretation of a genuine void. In later work, formal void-finding methods help make this process more systematic. Different algorithms may define centers and edges somewhat differently, but they share the central goal of identifying large connected regions of low galaxy density within a surveyed volume. Selection effects must always be considered. A survey may be limited by brightness, which means faint galaxies at greater distances are less likely to be included. The observed scarcity in a region could therefore be exaggerated if the survey is incomplete. Astronomers compensate by defining samples carefully, comparing like with like, and testing how the results change under different assumptions. This is one reason why the mapping of voids improves over time. Better instruments, wider sky coverage, deeper catalogues, and more refined statistical tools all help distinguish real cosmic emptiness from observational weakness. Even with these improvements, a void remains something inferred from traces. Galaxies are the main visible markers used in many surveys because they are bright enough to be catalogued across vast distances. Yet galaxies do not represent all matter directly. They mark the places where structure grows strongly enough for luminous systems to form and persist. A mapped void is therefore first a region with very few galaxy traces. Its deeper matter content is a further question, but the initial recognition comes from the pattern of visible systems. This makes galaxy catalogues the practical doorway through which the emptiest large regions enter scientific knowledge. As mapping techniques improve, the picture becomes richer rather than simpler. A void that once seems roughly spherical may show a more irregular shape. A region thought to be one large hollow may reveal substructure within it. Another may turn out to connect with neighbouring sparse zones. Yet this complexity does not undermine the original method. It confirms its strength. The map does not invent the void, it refines it. Each new survey adds resolution to a structure that is already present in the galaxy distribution. The discovery and mapping of giant voids therefore belong to one of the quiet revolutions of modern astronomy. The universe changes in appearance when distance is measured carefully enough. What once looks like a sky filled with scattered island galaxies becomes a three-dimensional web with major empty interiors. The emptiest places are not seen directly as objects. They are revealed by the disciplined placement of many galaxies into space. From that measured arrangement, the void emerges as a real region, broad and coherent, defined not by darkness alone, but by the orderly absence of expected structure. The word empty carries more weight in ordinary language than it does in cosmology. In daily life, an empty room is expected to contain nothing of importance. An empty glass holds no water. An empty road has no traffic. These uses train the mind to imagine emptiness as a clean absence, a place where contents have been removed and where nothing remains except the bare container. The universe does not offer emptiness in that simple form. When astronomers describe a giant void as empty, they are using a comparative word. They mean that a region contains far less matter than average, not that it contains no reality at all. This distinction matters because the large-scale universe is measured statistically. A cosmic void is identified by comparing one region with the mean density of matter or with the expected abundance of galaxies in a similar volume. The word average becomes central here. The average does not describe what every region looks like. It describes the typical amount of matter spread across a very large sample of space. A void is empty only relative to that wider standard. It is underdense. It falls below the mean. Its emptiness is therefore not absolute, but proportional and measurable. Once this is understood, the phrase emptiest place in the universe becomes more precise. It does not point toward a place where existence stops. It points toward a place where the density of matter is reduced to an extreme degree compared with the rest of the observable cosmos. That reduction may be profound. It may extend across an immense volume. It may leave only a thin residue of galaxies and diffuse material, yet residue still matters. The concept remains anchored in scarcity rather than erasure. Empty means less, not none. This is one reason why giant voids remain part of the normal universe rather than exceptions standing outside it. They share the same expanding space, the same gravitational history, and the same underlying physical laws as richer regions. The difference lies in how much matter gathers there over cosmic time. In a dense cluster, matter accumulates strongly. In a void, matter gathers weakly and often drifts toward denser surroundings. The contrast can become very large, but it does not create a separate category of existence. A void is still a region of the universe. It is simply one in which the known contents of the universe are much thinner than usual. The idea of absolute nothingness is also difficult in physics for another reason. Space itself is not merely an empty stage. It has geometry, expansion, and physical properties that can be described mathematically and observed indirectly. Light crosses it. Gravity acts through it. Fields exist within it. Even a place with no stars, no planets, and no visible galaxy nearby would still belong to the physical fabric of the cosmos. In this sense, the language of nothing becomes misleading very quickly. A void can be extraordinarily sparse while still remaining fully embedded in a structured and active universe. Ordinary matter also does not disappear entirely from such regions. Matter in the universe is not confined to bright objects alone. Stars and planets are dramatic examples, but they represent only part of the total content of ordinary matter. Much of that matter exists as diffuse gas spread between galaxies, often so thin that it is difficult to detect directly. In a giant void, that gas becomes even more rarefied than elsewhere, yet the possibility of its presence remains important. A region may look empty because it lacks luminous systems, while still containing trace material so sparse that it barely leaves an observational mark. This does not weaken the emptiness, it defines its real physical meaning. Radiation also passes through these vast regions. Light from distant galaxies crosses them. The cosmic microwave background fills all directions as a faint afterglow from the early universe. Other weak backgrounds and particles move through cosmic space as well. These do not crowd a void in the way galaxies crowd a cluster, but they remind astronomy that no large region of the observable universe becomes a perfect blank. Even great sparsity exists within a sea of physical processes that continue everywhere. The emptiest regions are calm, not non-existent. This is why astronomers rely on careful phrases such as underdense region, rather than purely dramatic language. The scientific vocabulary protects an important balance. It allows the depth of the scarcity to be recognized without inviting the false impression that a void is a gap in existence itself. A giant void can be one of the most extreme low-density environments known and still contain matter, radiation, and gravitational structure at very low levels. The word empty is acceptable only when this balance is kept in mind. There is also a useful difference between visual emptiness and physical emptiness. A region may look empty in a survey because few bright galaxies are present. That is visual emptiness at the level of luminous traces. Physical emptiness asks a deeper question about all matter and energy within the region. The two ideas overlap, but they are not identical. A place with very few visible galaxies is usually underdense in a broader sense as well, yet not every component becomes equally scarce. Some faint gas may remain. Dark matter may still thread through the region at reduced density. Radiation may continue to pass across it. The meaning of empty, therefore, depends on what exactly is being counted. This layered meaning explains why cosmic emptiness remains a scientific subject rather than a simple label. A void is not just a place where astronomers fail to find enough galaxies. It is a region whose low density tells a story about structure formation, matter flow, and the uneven growth of the universe. The emptiness has content in the form of information. By being less full, the region becomes more informative. It reveals how the cosmic web develops contrast, and how the average distribution of matter can produce extremes without ever reaching pure nothing. The phrase emptiest place in the universe therefore becomes calmer and more exact when stripped of everyday assumptions. It refers to the deepest known reduction of cosmic contents across a vast region, not to the vanishing of all physical reality. A void remains part of the same universe as clusters and galaxies. It shares the same space, the same history, and the same laws. What changes is density. Matter becomes thin enough that absence dominates the description, even though presence never disappears completely. In cosmology, empty is real, measurable, and profound, but it is never simple nothing. Even the deepest known cosmic voids do not remain entirely without galaxies. A sparse population persists within them, scattered across enormous distances and living under conditions very different from those found in richer parts of the cosmic web. This small population is important because it shows that underdensity does not erase structure completely. Instead, it changes the kind of structure that can grow and how often it appears. Inside a giant void, galaxies become uncommon enough that each one seems less like part of a crowded society and more like an isolated settlement spread across a vast, quiet interior. This rarity is one of the clearest marks of a void. In a denser region, galaxies often appear in groups, clusters, and connected chains. Their mutual proximity allows gravity to shape shared environments. Gas can be drawn into common wells of attraction. Smaller galaxies may orbit larger ones. Encounters become more frequent. In a void, those conditions weaken. The average separation between galaxies becomes much greater. A galaxy may spend cosmic time with few close neighbors. The surrounding large-scale environment offers less external pressure, less crowding, and fewer opportunities for strong interaction. The difference is not merely numerical, it becomes a difference in lived cosmic setting. The galaxies that inhabit voids are therefore studied as members of a special environment. They are usually not the giant central systems that dominate rich clusters. More often they are smaller and less tightly packed into large communities. Many are modest spiral or irregular systems rather than the most massive galaxy types seen in dense nodes of the cosmic web. This pattern does not mean that a void forbids large galaxies entirely. It means that the underdense setting makes the growth of rich, crowded galactic systems less common, where matter is scarce on large scales. The paths that lead to especially massive and socially connected galaxies tend to be less favored. Isolation changes behavior over time. In richer regions, galaxy encounters and mergers can strongly shape a galaxy's history. A merger is the gradual coming together of two galaxies under gravity, until they combine into one system. In a void interior, such events usually become less common because potential partners are farther away. A galaxy there may evolve more quietly, influenced more by its own internal reserves of gas and star formation than by repeated collisions with neighbors. This gives void galaxies a certain scientific clarity. They can provide a view of galactic development with less interference from the crowded social life that shapes galaxies elsewhere. That quiet does not mean inactivity. Stars still form inside some void galaxies. Gas still cools, rotates, and gathers in clouds. Supernova explosions still return material to surrounding space. Black holes may still exist at galactic centers. Ordinary galactic processes continue, but they do so within a thinner outer environment. The void does not suspend known physics. It lowers the frequency of external disturbance. This can make a void galaxy seem calm in comparison with a similar galaxy living near many companions, even though the internal life of stars, gas, and gravity remains active. The small number of galaxies inside a void also helps astronomers measure how deep the underdensity truly is. A void is not defined only by empty volume. It is also defined by the weakness of its visible population compared with the expected population of a more typical region. Every confirmed galaxy within the interior matters because it sharpens the statistical picture. A few galaxies do not destroy the concept of the void. They reveal its true character. The interior is not a blank chamber. It is a wide region in which the galaxy population has been reduced to a sparse and scattered remnant. Some of these galaxies appear to line up loosely along thin internal threads, or to gather near the less empty parts of a void rather than at its deepest center. This is consistent with the broader logic of structure formation. Even inside an underdense region, density is not perfectly uniform. Some locations are slightly richer than others. Where matter is a little less scarce, a small galaxy can still form and persist. The interior of a void is therefore not featureless. It contains subtle variations, and the few galaxies that remain often trace those faint differences. Their positions offer clues about how little structure can survive in a very thin cosmic setting, because the environment is gentler in some respects. Void galaxies have often been considered useful for studying how galaxies behave when outside influences are weaker. A galaxy in a dense cluster lives among frequent gravitational encounters, hot surrounding gas, and strong environmental effects. A galaxy in a void interior experiences a different balance. It may retain gas for longer. It may continue forming stars in a steadier way if enough fuel remains. Its shape may reflect a quieter history of assembly. These tendencies are not absolute rules, but they reveal why underdense environments matter. The void becomes not only a place of scarcity, but also a place where a galaxy's surroundings exert a more delicate hand. The great separations inside a void also reshape any intuitive sense of neighborhood. In a rich galaxy environment, nearby systems can define the local sky in important ways. In a deep void, the nearest substantial neighbors may lie much farther away. This does not mean the sky within a void is dark in a total sense, because distant light from the wider universe still crosses the region. It means that the local galactic community becomes thin. The few galaxies that exist inside the void inhabit a broad silence between one another. Their rarity is measured not only by count, but by distance. This sparse population helps correct a common misunderstanding. The presence of any galaxies at all might seem to weaken the claim that a void is an emptiest place. In fact, the opposite is true. The few galaxies inside a void give the idea of emptiness its real physical form. They show that the interior belongs to the same universe as everywhere else, yet in a greatly reduced state. Their survival proves continuity. Their scarcity proves extremity. Without them, the subject would drift toward the language of pure nothingness. With them, the subject remains grounded in measurable cosmology. The galaxies of a void also carry a quiet dignity. They exist where the cosmic web offers little support, little crowding, and little abundance. They form and evolve in a region where matter has largely flowed elsewhere. They remain as scattered witnesses to a long process of gravitational sorting. Their small number tells astronomers how strongly the environment has been emptied. Their continued presence tells astronomers that even the thinnest great regions of the universe still allow islands of structure to endure. In this sparse interior population, emptiness becomes more exact. A giant void is not a place where galaxies vanish completely. It is a place where galaxies become so few, so separated, and so lightly embedded in the larger web that their rarity itself defines the region. The underdense environment does not remove cosmic life. It thins it to a quiet remnant. Through these few galaxies, the void shows its true scale, its restraint, and its place within the larger order of the universe. Beyond the few visible galaxies that remain inside a giant void, a deeper layer of structure still persists. This layer does not shine. It does not form bright spirals, glowing clusters, or luminous walls. It is dark matter, the unseen mass whose presence is inferred through gravity rather than direct light. In the great sparse regions of the cosmic web, dark matter becomes thinner just as visible matter becomes thinner, yet it does not vanish. The hidden framework of the universe continues through the void in a reduced and delicate form. This matters because the emptiness of a void is not only a reduction in visible galaxies, it is also a reduction in the invisible matter that helps shape the large-scale cosmos. Dark matter is called dark because it does not interact with light in the ordinary ways that allow stars, gas clouds, and galaxies to be seen directly. Telescopes register light from ordinary matter, but dark matter reveals itself mainly through gravitational effects. Galaxies rotate in ways that suggest more mass than their visible parts contain. Clusters of galaxies bend light more strongly than luminous material alone can explain. The growth of a large-scale structure across cosmic time also points to an unseen gravitational component. This invisible mass becomes one of the central ideas of modern cosmology because it helps explain why the cosmic web forms as it does. In a dense region of the universe, dark matter gathers into strong concentrations called halos. A halo is a gravitational structure in which matter is bound together, providing the framework around which galaxies can form. Rich galaxy clusters contain many such halos and often sit within even larger dark matter concentrations. Filaments also owe much of their structure to the distribution of this unseen mass. When a giant void forms, the opposite tendency appears. The void does not lose dark matter completely, but it contains far less of it than the cosmic average. Its hidden scaffolding becomes thinner and less able to support the growth of many bright galaxies. This reduced dark matter density is essential to the logic of emptiness. A void is not merely a place where stars fail to light up. It is a place where the underlying gravitational framework itself is undernourished. Ordinary matter follows gravity. It drifts toward regions where the total mass, including dark matter, is greater. If the dark matter in a broad region remains sparse, then gas and other ordinary matter have less reason to gather there strongly. Over time, the void deepens. Matter leaves more readily than it arrives. The visible scarcity of galaxies therefore reflects a deeper scarcity in the unseen distribution beneath them. Yet thin does not mean absent. Dark matter still threads through a void, though more gently and unevenly than in richer environments. The interior of a giant void is not a blank volume with no gravitational structure at all. It contains low-density dark matter spread across vast scales, along with smaller fluctuations within that broader thinness. Some parts of the interior may be slightly denser than others. Those modest variations can help explain why a few isolated galaxies still manage to form inside the void. Even a very reduced dark matter environment is not perfectly smooth. The few surviving galaxies often mark the places where the hidden framework, though weak, is still somewhat stronger than its surroundings. This subtle structure gives the void a quiet complexity. From the outside, it may seem as though emptiness has simply replaced matter. At a deeper level, the void is better understood as a region where the same hidden cosmic material continues in diminished form. The difference between a filament and a void is therefore not the presence of dark matter in one, and its total absence in the other. The difference lies in degree, concentration, and gravitational influence. A filament is rich in the unseen mass that channels growth. A void holds that same component in a much lower density, so the power to gather ordinary matter becomes much weaker. Simulations of cosmic structure help illuminate this picture. When astronomers use known physical laws and cosmological conditions to model the growth of the universe over time, dark matter naturally forms a web-like pattern. Dense knots and filaments emerge alongside wide, underdense interiors. In these models, voids are not gaps torn free from the dark matter network. They are the thinnest parts of that network. The hidden material stretches through them in low concentration while draining towards surrounding structures. This gives a coherent explanation for why voids and boundaries grow together. The bright walls of galaxies around a void correspond to regions where dark matter becomes richer, while the quiet interior remains a domain of weakened gravitational support. The presence of dark matter in voids also keeps the subject grounded in ordinary cosmology. Without it, one might imagine a void as a place where known structure simply ends. The hidden mass prevents that misunderstanding. Even the emptiest large regions remain connected to the broader cosmic system through gravity. They continue to participate in expansion, in structure formation, and in the long redistribution of matter. Their extreme thinness does not separate them from the universe. It shows how far the same general process of uneven growth can proceed, because dark matter is invisible. The study of its behavior inside voids requires inference rather than direct inspection. Astronomers compare galaxy distributions, test cosmological models, and examine how mass should evolve under gravity across long spans of time. Weak gravitational lensing, in which mass bends passing light by a small amount, can also contribute information about mass distribution on large scales. Through such methods, the quiet conclusion emerges that voids are genuinely underdense in total matter, not only in luminous material. Their emptiness goes below the surface of what the eye can see. This hidden underdensity helps explain why the galaxies inside a void are so rare and so widely separated. The visible population is not merely sparse by chance. It reflects a deeper shortage in the invisible mass needed to support stronger clustering and richer growth. A void galaxy lives where the hidden foundation itself is thin. It rises from a faint part of the cosmic framework rather than from one of its strong beams. This makes the few galaxies inside a void even more informative, because they reveal where low-level structure persists inside the reduced dark matter field. Dark matter also gives the emptiness of a void a kind of firmness. The void is not only a visual impression created by missing lights, it is a real underdensity in the mass content of the universe. That mass is mostly unseen, yet it governs much of the cosmic architecture. When a region is poor in dark matter, it becomes poor in gravitational opportunity. Ordinary matter gathers less effectively. Galaxies become fewer. The sparse interior takes shape. In this way, the hidden material defines the visible emptiness. Within the great quiet of a cosmic void, dark matter remains as the faintest structural layer still spread through the region. It is reduced, stretched thin, and far less concentrated than in the bright boundaries outside. Yet it endures. The emptiest places in the universe are therefore not hollow shells of nothing. They are the weakest reaches of a larger hidden framework, places where even the invisible mass of the cosmos falls to a low and delicate minimum while never disappearing entirely. Between the few galaxies that inhabit a giant void, another layer of matter remains. It is not gathered into bright stars or obvious galactic disks. It does not announce itself with concentrated light. It exists as diffuse intergalactic gas, spread so thinly across enormous distances that its presence is difficult to detect and easy to underestimate. In the emptiest great regions of the universe, this gas becomes one of the quietest forms of ordinary matter. It does not fill the void in any crowded sense, but it prevents the region from becoming a place of literal nothingness. Even where galaxies are rare and dark matter is greatly reduced, ordinary matter still lingers in a trace-like state between the islands of visible structure. This gas belongs to the broader baryonic matter of the cosmos, the ordinary matter made of protons, neutrons, and electrons. Much of it is not locked inside stars or planets. On the larger scales, a significant share of ordinary matter lives outside galaxies, spread through the intergalactic medium. A medium is simply a material filling or occupying a space. In this case, it refers to the thin gas that exists between galaxies across the vastness of cosmic structure. In rich regions of the cosmic web, this gas can be drawn into filaments, heated by gravitational collapse, or enriched by material thrown out from galaxies. In a void, the same basic substance remains present in far lower density, extended across a quieter and more weakly structured environment. The thinness of this gas is difficult to imagine because ordinary experience does not provide a close comparison. Air on Earth, even at high altitude, is dense beside the intergalactic medium. The gas inside a cosmic void is so rarefied that individual particles can be separated by great distances on microscopic scales, and yet across the enormous total volume of the void, those particles still amount to a real, though faint material presence. Emptiness at cosmic scale is therefore a matter of density rather than complete removal. The gas becomes extraordinarily dilute, but dilution is not disappearance. This diffuse matter does not gather easily into stars within the broad interior of a void because the conditions that encourage strong collapse are weak there. Gravity has already drawn much matter toward surrounding filaments and walls, leaving the void interior with less fuel and less concentrated structure. What remains is spread thinly, often too thin to cool and condense into new luminous systems, except in the rare places where local conditions become slightly more favourable. The gas in a void therefore helps explain why the region contains so few galaxies. Ordinary matter is present, but it is stretched across such a large and undernourished environment that galaxy formation becomes uncommon. Some of this gas may be warm or hot, depending on its history and on the broader state of the intergalactic medium. Temperature in such settings does not mean warmth in the familiar human sense. It reflects the motion and energy of particles. Gas between galaxies can be heated by large-scale structure formation, shocks, and radiation, even when it remains so thin that it would feel nothing like ordinary heat if one tried to imagine standing within it, in a void. The gas often avoids the strongest heating found in denser collapse structures, yet it is still part of the wider thermal history of the universe. It carries memory of expansion, weak interactions, and past cosmic change. Its detection is difficult precisely because it does not shine strongly. Astronomers often infer the presence of diffuse intergalactic gas by studying how it absorbs light from more distant objects. When light from a bright distant source passes through thin gas, certain wavelengths can be absorbed by the atoms or ions in the material along the line of sight. An ion is an atom that has gained or lost electrons. These absorption signatures allow astronomers to sense gas that would otherwise remain almost invisible. In this way, a void may reveal part of its faint ordinary matter, not by emitting a glow of its own, but by leaving delicate marks upon light that crosses it. This method reinforces an important lesson. A giant void does not need to contain bright matter in order to contain meaningful matter. The diffuse gas between galaxies may be so sparse that it contributes almost nothing to the visual richness of the region. Yet it remains part of the physical content of the void. It also helps connect the subject of cosmic emptiness to the broader problem of where ordinary matter resides in the universe. Since much baryonic matter is not stored inside stars or galaxies, the study of underdense regions must include these extremely thin gaseous components. The void becomes less like an absent place, and more like a place where ordinary matter survives in one of its faintest large-scale forms. The gas is also not necessarily distributed perfectly evenly within the void. Even a sparse region can contain gentle gradients, slightly denser strands, or subtle internal variations shaped by the long history of matter flow. A few of the rare galaxies within a void may sit where the gas and underlying gravitational structure are marginally stronger than average for that interior. Most of the region remains deeply underdense, but not mathematically uniform. This quiet texture matters because it preserves continuity with the rest of the cosmic web. The void is an extreme environment, but it is still shaped by the same uneven processes that organize matter everywhere else. There is a calm irony in this. The emptiest place in the universe may still hold one of the largest reservoirs of ordinary matter in a very diluted form, simply because the region itself is so immense. A tiny density spread across an enormous volume can still amount to a significant total content, even though any local patch remains profoundly sparse. This does not make the void less empty in the scientific sense. It makes its emptiness more subtle. The matter is present as a whisper rather than a crowd, as a trace rather than a structure, as a thin intergalactic remnant rather than a luminous population. This diffuse gas also moves with the wider cosmic story. It expands with space on large scales. It can drift under weak gravitational influence. It can be ionized by background radiation, enriched in small measure by material leaving galaxies, or left in a more pristine state than gas in crowded environments. The void interior therefore contains not only fewer objects, but a quieter history of material processing. It is a place where ordinary matter often remains less transformed by repeated galactic activity and more stretched out by the long geometry of the evolving universe. Within a giant void, then, emptiness becomes materially precise. Between the rare galaxies lies not a clean void of absolute nothing, but a vast reach of extremely thin intergalactic gas. It is difficult to see, difficult to measure, and easy to forget beside the bright drama of stars and galaxies, yet it remains one of the defining components of the underdense interior. The emptiest regions of the universe are not empty because all ordinary matter has gone. They are empty because that matter has been reduced to one of its most diffuse and quiet states, spread across immense distance until presence nearly disappears into rarity. A giant void appears dark when compared with the crowded boundaries of the cosmic web. Yet darkness in the universe is never complete. Even in the most underdense known regions, light still passes through. Radiation still fills space. The sparse interior may contain very few nearby galaxies and only the thinnest diffuse gas, but it is not sealed off from the rest of the cosmos. Photons, the particles of light, continue their long journeys across it. The emptiest place in the universe is therefore not a chamber without illumination in an absolute sense. It is a region where local sources of light are greatly reduced, while the wider radiative presence of the universe remains. This distinction begins with the difference between local brightness and background radiation. A dense cluster of galaxies contains many stars, glowing gas, and sometimes powerful active galactic centers. Such a place can be rich in nearby light sources. A giant void offers much less of that local radiance. Its few galaxies are widely scattered, and much of its enormous volume contains no luminous system nearby at all. If one imagines standing within such a region, the local environment would be far quieter in visible structure than the interior of a galaxy-rich wall. Yet the larger universe would still surround it. Light from distant galaxies would continue to cross the region from many directions. The absence of local abundance does not erase the passage of remote light. One of the most important forms of radiation present everywhere is the cosmic microwave background. This faint glow is the relic light from the early universe, released when the cosmos cools enough for light to travel freely through space. It does not belong to stars or galaxies in the ordinary sense. It belongs to the deep history of the universe itself. It arrives from all directions and fills even the emptiest large-scale regions. A void does not escape it. The cosmic microwave background is one of the clearest reminders that cosmic emptiness never means disconnection from the whole. Even the most underdense region remains immersed in the afterglow of the early cosmos. This background radiation is not visually bright in the ordinary sense. It lies in microwave wavelengths and requires instruments to measure it properly. Yet its presence is physically real and cosmologically central. It supplies a uniform radiative field against which later structures form and evolve. In a giant void, the cosmic microwave background remains one of the most universal components of the region. It does not care whether galaxies are abundant or scarce nearby. It simply continues across the whole observable universe, passing through filaments, clusters, and void interiors alike. In this way, the emptiest places remain lit by the oldest broad light the cosmos still carries. Other background light also crosses these regions. Stars in distant galaxies produce radiation across many wavelengths. Active galactic nuclei, where matter falls toward massive black holes and releases intense energy, can contribute as well. This light may be faint when averaged across a vast void, but it does not disappear. The interior of a giant void lies open to radiation from beyond its boundaries. Since the region is so large and so thin, photons can move through it with little interruption from matter. The emptiness that removes local sources can also make the interior more transparent to radiation passing across cosmic distances. Transparency is a useful word here. A transparent medium allows light to pass through with relatively little absorption or scattering in a dense cloud of gas or dust. Transparency may be low because many particles interact with the light. In a giant void, the density of matter is so small that the region becomes, on large scales, remarkably open to the passage of radiation. This does not mean nothing happens there. It means that the few particles present are too sparse to block much of the light crossing the region. A void becomes not only a place of reduced matter, but also a long corridor through which cosmic radiation can travel. The darkness of a void, therefore, has a relative meaning similar to the emptiness of a void. It is dark because nearby luminous sources are rare, and because the interior lacks the rich concentrations of stars and glowing gas found elsewhere. It is not dark because all light has been extinguished. The sky inside such a region, if imagined from a stable point, would still contain distant galaxies and the accumulated radiative backgrounds of the universe. The visual impression might be one of extreme separation and low local brightness, but not of perfect black isolation. Cosmic light is too widespread and too persistent for that. Radiation also continues to shape the physical state of the thin matter within the void. Background photons can ionize atoms under suitable conditions. Energy carried by radiation contributes to the thermal and ionization history of the intergalactic medium. Even in low-density regions, the few particles present do not exist in total radiative silence. They remain exposed to the wider field of cosmic energy. This is another reason the language of absolute emptiness fails. A void contains little matter, but that little matter still participates in a universe filled with travelling radiation. The weakness of local light inside a giant void nevertheless matters deeply. It helps define the character of the region. In the brighter boundaries of the cosmic web, many galaxies shine close enough together to create obvious structure in maps and surveys. In the interior, the long stretches between luminous systems create a different condition. Distance dominates. Brightness becomes diluted by separation. Any one galaxy may shine normally by its own nature, yet across the large volume of the void the distribution of luminous sources becomes so thin that darkness takes on structural importance. The region is dark not because light is absent everywhere, but because light-producing objects are too few and too far apart to overcome the vastness between them. This balance between darkness and radiation gives the void one of its most subtle qualities. It is a place where the absence of nearby structure becomes visible against the continued presence of universal backgrounds. locality grows quiet while the cosmos as a whole remains active. A few photons from a distant galaxy can cross a region that contains almost no local galaxies at all. The relic glow of the early universe can pass unchanged through a domain nearly empty of ordinary structures. The great sparse regions thus teach a calm lesson. Cosmic darkness is often the darkness of reduced neighborhood, not the darkness of abolished physical connection. Even the emptiest large regions remain woven into the luminous history of the universe, ancient radiation from the early cosmos, faint light from distant galaxies, and energy crossing vast stretches of space all continue to inhabit them. A void reduces local brilliance to a minimum, but it does not cancel illumination entirely. Its darkness is real. Yet it is a darkness within a radiative universe. In the broad silence of the giant void, light still travels, backgrounds still endure, and the emptiest place remains gently threaded by the faint but unbroken glow of cosmic existence. When the contents of a giant void are reduced below galaxies, below dark matter concentration strong enough to host rich structure, below even the thin spread of intergalactic gas considered as a broad medium, what remains is matter in its faintest large-scale traces. These traces are not gathered into familiar objects. They are not arranged into luminous systems. They exist as scattered particles, dilute plasma, lonely atoms or ions, and weak streams of matter passing through the vast interior. At this level, the emptiest place in the universe approaches the practical floor of cosmic material presence. It still does not reach absolute nothingness. Instead, it reveals how matter can survive in forms so sparse that presence becomes almost indistinguishable from absence. A particle is a very small unit of matter or radiation. In the context of a void, the most relevant material particles are the basic constituents of ordinary matter and the thin remnants of ionized gas. Ionized gas, called plasma, is a state in which electrons are not fully bound to atoms. A plasma can be dense and hot, as in stars, or it can be extremely thin and quiet, as in intergalactic space. Inside a giant void, plasma exists in the latter form. It does not resemble a glowing fire or a brilliant electric discharge. It is so rarefied that its particles may travel immense distances before interacting. Yet the condition remains physically real. The emptiest large regions of the universe still contain matter as scattered charged particles drifting through an enormous volume. This change in scale transforms the meaning of material presence. In a galaxy, matter gathers into stars, gas clouds, dust, planets, and compact objects. In a void boundary, it may still gather into galaxies and groups. In the deeper interior, much of that organized structure gives way to isolation. Electrons, protons, and ionized atoms remain separated across the vastness. Their density becomes so low that the usual human image of a substance no longer applies well. A substance on Earth fills a container or forms a surface that can be touched. The matter inside a giant void does neither. It exists more like a statistical sprinkling across great space than like a continuous body in the everyday sense. This sparse plasma is important because it carries some of the last remaining ordinary material content of the void. Even where galaxies are absent over huge distances, the void can still contain these individual particles. They may be remnants of the primordial matter left from the early universe, or matter gently influenced by radiation, weak shocks, and the long flow of structure formation. Some may have been enriched in small measure by elements that originate in stars and later escape galaxies into intergalactic space. Others may remain closer to simpler states shaped mainly by cosmic expansion and diffuse ionization. The details vary, but the main fact remains steady. Matter survives in the void by becoming thin enough to lose the appearance of a coherent medium while retaining physical existence particle by particle. The motion of these particles is also unlike the motion of matter in dense environments. In a crowded gas cloud, collisions happen often. In a star, particles interact constantly. In a giant void, interactions become rare. A proton or electron may travel through long distances before meeting another particle in a significant way. This does not make the void inactive. It makes activity sparse and spread out over vast scales. The interior becomes a place where matter exists, moves, and responds to fields and radiation with great patience. The rhythm of interaction slows because separation becomes one of the defining conditions of the region. At this level, the distinction between gas and particle begins to blur. A gas is usually imagined as many particles moving together in a shared space, in a deep void. The gas remains so dilute that describing it as individual particles can sometimes feel more natural than describing it as a fluid-like medium. Yet both descriptions have value. The fluid view helps astronomers model large-scale distributions and thermal properties. The particle view helps the mind understand just how far emptiness has progressed. Matter is still present, but not in a crowded enough form to resemble familiar material environments. The void approaches the minimum practical density at which matter still participates in cosmic physics. A few additional particles also cross such regions without forming local structure. Neutrinos, for example, stream through the universe in enormous numbers, though they interact so weakly with ordinary matter that they are extraordinarily difficult to detect. Their presence does not fill a void in the sense of creating structure or substantial local density. But it reminds physics that even the most underdense regions are crossed by elusive material components. High-energy particles from distant energetic events may also pass through. These passing traces do not settle the question of emptiness by making a void crowded. They simply deepen the lesson that the universe does not provide perfect blankness. It provides degrees of rarity. The charged particles within a void also respond to electromagnetic conditions, though these are weak on large scales in such an underdense environment. A free electron is still an electron. An ion is still sensitive to fields and radiation. Plasma, however thin, still belongs to the electromagnetic life of the cosmos. This is another way in which the deepest emptiness remains physically connected to the wider universe. The particles are few, but they are not cut off from law, motion, or influence. They remain part of a cosmos in which even slight traces can matter across great distances and times. What is most striking is how little material is needed to prevent true nothingness. A handful of particles spread across an enormous region, or even a density so low that it almost escapes description, is enough to keep the void within the domain of physical presence rather than total absence. The emptiest place in the universe is therefore not defeated by a few surviving particles. It is defined by the fact that such particles are nearly all that remain when richer structures have drained away. Emptiness reaches its practical depth when matter is reduced to this whispering level. This smallest material scale also gives the void a quiet dignity. The region is not empty because it has been cleared like a room. It is empty because cosmic history has drawn matter outward into brighter structures and left behind only the thinnest residue. The remaining particles are the final witnesses of that process. They mark the point at which structure has almost ceased, while still preserving a faint material continuity with the rest of the observable universe. They are too few to build a galaxy-rich environment, too thin to dominate the region, and yet real enough to keep the void within the fabric of known nature. At this depth, the concept of emptiness becomes almost exact without ever becoming absolute. The giant void contains matter reduced to scattered particles, tenuous plasma, and passing material traces that barely register against its enormous volume. This is the floor beneath which ordinary cosmic emptiness struggles to go. The universe allows matter to become astonishingly sparse, but it does not easily permit a region to become pure nothing. In the deepest quiet of the void, the last material traces remain, delicate and widely separated, showing how near the cosmos can come to emptiness while still holding on to existence. The emptiest place in the universe remains difficult to define with complete precision, because emptiness is not a simple object that can be pointed to and measured like the diameter of a planet. It is a condition inferred from comparison, and comparison depends on method. Astronomers do not begin with a region labelled empty in nature itself. They begin with surveys, catalogues, redshift measurements, brightness limits, and statistical choices. From these, underdense regions are identified. The difficulty arises because each step contains limits, and the final picture of emptiness depends on how those limits are handled. A void does not come with a painted border. Its edge is usually gradual rather than sharp. In one place, galaxy density may be very low. Farther outward, it may rise slowly. In another direction, the rise may be quicker. The surrounding wall may be rich and obvious on one side, while more broken and uncertain on another. This makes the boundary of a void partly physical and partly definitional. The region is real, but the exact line at which one chooses to say the void ends is often shaped by the method of analysis. One study may draw the boundary somewhat wider, another somewhat tighter, and both may still be describing the same broad underdense structure. The problem grows because astronomers usually identify voids through traces rather than through direct knowledge of all matter. Galaxies are the most common traces because they can be catalogued across large distances, yet galaxies are not matter in its entirety. They are the luminous peaks of structure, the visible systems that form where conditions allow. A region with very few catalogued galaxies is usually underdense, but the exact degree of underdensity depends on how faithfully those galaxies represent the deeper matter distribution. If the traces are sparse, biased toward brighter objects, or incomplete in certain areas, then the inferred emptiness can appear deeper or shallower than it truly is. Brightness limits are especially important. Every survey has a threshold below which faint galaxies are difficult or impossible to detect. A nearby region may reveal many small and dim systems that a more distant region would hide. If those missing faint galaxies are not accounted for properly, a far region can seem emptier than it really is. Astronomers work carefully to reduce this problem by constructing controlled samples, comparing only regions that are measured under similar conditions, and correcting for known limits. Even so, the emptiest place remains partly dependent on what the instruments can reach. Better surveys do not merely sharpen the picture, they can alter the ranking of which region seems most extreme. Distance measurement introduces another layer of difficulty. Redshift gives a powerful estimate of distance, but the observed redshift of a galaxy includes not only the large-scale expansion of the universe, but also the smaller motions of galaxies within their local gravitational environments. These additional motions can slightly shift the inferred position of a galaxy along the line of sight. On the scale of a giant void, the overall structure remains visible, but fine details of its depth and shape can be distorted. A boundary may appear stretched or compressed. A region may look more coherent or less coherent depending on how these effects are treated. The void is real, but its exact geometry is never read from nature without interpretation. There is also the issue of method. Different void-finding algorithms use different rules for deciding what counts as a void. Some search for large, nearly empty spheres that can fit inside the galaxy distribution. Others identify connected basins of low density with more flexible shapes. Some emphasize the deepest interior regions. Others include broader surrounding zones where density remains below average, but not at the lowest level. Because of this, one catalogue may list a region as a single immense void, while another may divide it into several linked subvoids. Neither approach is necessarily careless. They simply reflect different ways of translating a complex underdense landscape into formal description. The very word emptiest adds another complication. One region may be larger, while another may be deeper at its centre. One may contain fewer bright galaxies, while another may contain less total inferred matter. One may look more extreme in a particular survey because of better contrast with surrounding structures. This means that emptiest is not always a single mathematical ranking. It depends on whether the emphasis falls on volume, central depth, average density deficit, luminous traces, or total mass content. Nature provides the underdense regions, but human analysis decides which property receives the strongest weight. Survey coverage also remains uneven in practice. Some parts of the sky are mapped more deeply than others. Some surveys focus on particular ranges of distance. Dust and stars within the Milky Way can obscure certain directions and make extragalactic mapping harder there. A giant void found in a well-studied region may become famous partly because it is well measured, while an equally impressive region in a more difficult direction may remain less certain or less recognized. The map of emptiness is therefore shaped not only by the universe itself, but by the directions in which observation becomes easier or harder. Time adds another subtle limit. Looking far away means looking into the past, and the observed galaxy population changes with distance, partly because the universe itself evolves. A nearby void and a distant void are not seen at the same cosmic age. Their comparison must therefore be made with care. A region that seems unusually empty at one epoch may not be identical in significance to a region observed at another. The emptiest place is always being assessed within a map that is also a record of different times. Even when observations improve, uncertainty does not disappear completely. Better data can reveal faint galaxies within a region once thought more vacant. A single broad void can resolve into a network of connected underdense pockets. A famous supervoid candidate can remain underdense while becoming less extreme than first claimed. Science does not fail in these revisions. It becomes more exact. The difficulty is not that emptiness is imaginary. The difficulty is that the universe presents emptiness with soft boundaries, layered contents, and survey-dependent visibility. For this reason, the emptiest place in the universe remains a careful scientific claim rather than a final dramatic title. Astronomers can identify regions of extraordinary underdensity with strong confidence, but the exact measurement of how empty, how large, and where precisely the edge lies remains tied to instruments, definitions, and statistical interpretation. The mystery endures not because nothing is known, but because so much depends on how known structure is measured against what is missing. At the innermost level of this subject, the emptiest place in the universe matters not only because it is sparse, but because it reveals how the universe builds itself A giant void is often described first as an absence, a region with fewer galaxies, less matter, and weaker structure than the cosmic average. Yet its deepest significance lies in what that absence measures. It records the long work of gravity, the role of dark matter, the distribution of ordinary matter, and the expansion history of the cosmos. The mystery remains because a void is not only a place, it is also a test. The first lesson it offers concerns structure formation. The large-scale universe begins in a much smoother state and slowly develops contrast. Dense regions grow richer, thin regions grow thinner. A giant void preserves one side of that transformation with unusual clarity. It shows how far matter can drain from a broad domain while still leaving behind a connected physical region, rather than a break in reality. In the crowded parts of the cosmic web, many processes overlap and complicate the picture. In a void, the thinness itself makes the long pattern easier to read. The region becomes a record of how scarcity grows when gravity has less to hold on to, and when surrounding structures steadily become better at drawing matter away. This gives voids special value in cosmology. They offer one of the quietest environments in which to examine the large rules of the universe. A crowded galaxy cluster contains intense local influences, frequent interactions, hot gas, and strong gravitational complexity. A giant void reduces much of that local noise. It does not remove physics, it removes abundance. In doing so, it allows astronomers to study how cosmic expansion and large-scale gravity shape matter under cleaner conditions. The emptiest regions therefore act like simplified portions of the cosmic web, where the main architecture can be studied with fewer luminous distractions. Dark energy enters the subject here as well. Dark energy is the name given to the unknown cause of the accelerated expansion of the universe. On the larger scales, this accelerated expansion affects how structure grows over time. Dense regions still gather matter locally, but the wider cosmic expansion increasingly shapes the overall evolution of large-scale patterns. Voids are sensitive to this history because their interiors are already underdense and relatively open. Their growth, shape, and distribution can therefore carry clues about how expansion proceeds across cosmic time. A void becomes more than a low-density region. It becomes a gentle tracer of the balance between matter's tendency to gather and the universe's tendency to expand. The study of voids can also test gravity itself. If the laws of gravity differed from the standard picture on the larger scales, voids might respond in subtle but detectable ways. Their profiles, motions, and relationships to surrounding structures could shift. For this reason, the emptiest regions are useful not only for confirming the familiar story of cosmology, but also for searching for small departures from it. A dense cluster may seem more dramatic, but a void can be more delicate and therefore more revealing. In a thin environment, slight changes in the rules can sometimes leave clearer marks. The sparse region becomes a quiet instrument for testing the strength and behavior of cosmic law. There is also meaning in the fact that emptiness resists final definition. The difficulty of naming one region as absolutely the emptiest known place is not a weakness of the science. It is a reflection of the richness of the universe and the care required to measure it. Boundaries are soft, traces are incomplete. Different properties compete for attention. One region may be larger, another deeper, another better measured. This uncertainty keeps cosmology honest. It prevents dramatic language from outrunning evidence. It also reminds astronomy that the universe is not arranged for simple rankings. Reality offers gradients, families of structures, and overlapping extremes rather than perfectly tidy labels. Voids also matter because they reconnect the idea of nothing with the idea of relation. In ordinary thought, nothing seems isolated and self-contained. A cosmic void is the opposite. It is defined by its relation to the average density of the universe, to the walls and filaments around it, to the dark matter beneath it, to the thin gas within it, and to the light that crosses it. Its emptiness is not solitary. It is structural. This makes the subject more subtle than it first appears. The void is not meaningful because it stands apart from everything else. It is meaningful because it reveals how everything else is arranged. The emptiest place in the universe therefore teaches a calm lesson about extremes. Nature does not need perfect absence in order to approach a limit. It allows matter to thin out across astonishing distances. It allows galaxies to become rare, dark matter to weaken, gas to become diffuse, and particles to survive only as traces. Yet it stops short of pure nothing. The extreme remains physical. The limit remains inhabited by law, radiation, and faint material continuity. This restraint is part of the beauty of the subject. The universe approaches emptiness without abandoning coherence. For astronomy, this means that voids are never merely empty scenery. They help refine maps of the cosmic web. They improve understanding of how matter flows over time. They offer a place to test models of expansion, structure growth, and gravity under conditions of profound sparsity. They also help answer a quieter philosophical impulse without stepping beyond science. When human thought asks how empty reality can become, the void gives the most measured answer available. It says that emptiness is real, immense, and meaningful, but never simple annihilation. It says that the cosmos remains a woven whole even where its threads grow faint. This final inner meaning returns the subject to mystery in its most disciplined form. The mystery does not survive because the void is magical or unknowable. It survives because the emptiest regions stand at the edge of measurement, definition, and interpretation while still remaining scientifically real. They are among the least crowded places known, yet among the richest in implication. By showing where matter almost ceases to gather, they reveal the power of the forces that gather it elsewhere. By showing how low density can fall, they illuminate the average from which that fall is measured. By holding on to the thinnest traces of existence, they show how deeply the universe remains connected to itself. The emptiest place in the universe is still a mystery because it's not merely a hole in the map. It is one of the map's finest tests. It is a region where absence becomes evidence, where rarity becomes structure, and where the quietest reaches of the cosmos still speak clearly about how the whole universe comes to be. The great void now rests in stillness. The distant walls of galaxies remain far away, faint and patient, while the interior holds its thin traces of matter, its passing light, and its long history of quiet expansion. Nothing rushes there. Nothing breaks the calm. The sparse region simply endures, suspended within the wider web of the cosmos, carrying the memory of matter that gathers elsewhere and of emptiness that deepens here. In that stillness, the largest structures of the universe begin to feel less like crowds of objects, and more like a single breathing pattern of abundance and scarcity. Bright knots grow where gravity gathers. Vast hollows open where matter becomes thin. Between them, the whole visible cosmos keeps its balance. Even the emptiest place belongs to that balance. It remains part of the same connected order as every star, every galaxy, and every drifting particle of intergalactic space. The mind settles on that wide quiet and finds no perfect nothing waiting there. Instead, it finds a gentler truth. The universe allows extreme silence, extreme distance, and extreme rarity, yet it keeps a faint continuity even in its most underfilled regions. A little matter remains, a little light still passes, the oldest background glow still crosses the dark. Emptiness becomes real without ever becoming absolute. So the void stays mysterious in the most peaceful way. It is known, yet not finished. It is measured, yet never reduced to a simple final claim. It remains a calm frontier inside the mapped cosmos, where absence teaches as much as presence, and where the farthest quiet continues without end into the patient night,